So on that handout that she gave you late yesterday, we've got a voltage drop, that's maximum length, length conductor. All right, we have one under number 1 and number 2. Number 1 is a single phase, so that's the one we'll do. We have a number 8 AUG running 200 feet to a 50 amp heating element with system voltage, single phase 240 volt. Okay? So I've got 240 volts on the circuit, got a number 8 wire, I've got 50 amps worth of draw current there, and we're looking for voltage drop. So the 2 guys represents, if I'm looking at this as a picture and I've got the panel here, my breaker here, in this case being single phase, and they're telling you got 200 feet, is that what it was? Just a number running right over here, 200 feet. That 200 feet is the distance from this breaker out to wherever that load is. Whatever that load of 50 amps is down here at the side here, that's 200 physical feet. Problem with that is that I've really got, if I've got 200 physical feet, I've got to have a pathway for it to go out there, first 200 feet, and then turn around and come back to the panel. Or in this case, if I've got 2 phases, I've got 2 paths. One way or the other, I've got 2 lengths of wire. Each length of that wire is 100 feet, or excuse me, 200 feet. So total length of wire then is 400 feet, and that's what that 2 does, is it doubles that, so it accommodates for the wire. Make sense? And the K being the resistive value of the wire means it doubles the resistive value of the wire, so we've got it all wrapped up in a nice nutshell. The only other number that we have to put up here, which instead of I really could look at it as A, but who's ever heard of 2 cads on the block, right? So, man, I tell you what. You look at that as, 2 KAD, I suppose, and some people even look at it as 2 cal, which is length in feet instead of D for distance, but that's always in feet is the way we express this, okay? But we look at the value we're talking about at 12.9 is ohms per 1,000 feet, not ohms per 1,000 inches or meters or whatever, so it's going to be 2 KID, the D being in feet, the I being in amps, the K being the resistive value of 2, so you can just plug in the numbers. At that point, we're just looking at 2 times 12.9 times 50 amps times 200 feet divided by 16,510? What's the number?
16,510.
16,510. Remember I said we're always looking for a bottom number, right? So I'm just going to cover that up. I'm going to take this number here and divide it into the top numbers. Make sure I multiply these out first. So 2 times 12.9 times 50 times 200, and then divide that 16,510 into it, and bada bing, do that.
So you're saying if they say copper, you know 12.9 goes for K.
Yep.
And if they say aluminum, it's the other.
Yep, that's it. There's no
Always.
difference. Yep. And if they don't say anything at all, it's 12.9. We'll always assume copper. They don't give you any other. It's like they just give you the wire size and say nothing else, which is happens quite a bit. There's actually a code reference for that back in 110. It's 110.5, I think, that tells you to always assume copper unless the statute dictates otherwise. So, all right. So what'd you get?
16.62.
And what is that number? The 16.62, is that what you're saying?
250.
Let me do it real quick.
Yeah, I'm gonna jack something.
That's not a trust y'all. 2 is 25.8 times 200 and times 50. So it gives me 258,000 on the top number. And then divided by 16,510. Gives you 15.62. All right, so I have a number then of 15.62. And what is that number? Did I lose 15%? Is that what that means? Because we talked about voltage drop in percentage, right? Usually, I mean, we're talking about voltage drop not less than 5% or not more than 3% or.
6.5.
Is that what it is? So what this is right here, guys, is the volts. It's the physical number of volts that you representatively lose in that distance. So if you put a meter here at 240 volts, down here you'd have 240 minus whatever this is at the actual load location. Okay? So to convert that, you just hit the division sign on your calculator, divide it by the system voltage of 240 volts, and what do you have? 0.000 something? Or 0.0 probably.
0.065.
240. And then to convert that to percentage with the decimal in 2 places, you get 6.5%, which is a little too much.
How did you get the 16,510?
It's 1562. Oh, no, this one right here?
Yeah,
Off of table 8, right there at the circuit mills for number 8 wire size there.
okay.
That's C in the inserted mills. And then that's why I was kind of telling you to put most of your, like your notes and stuff, voltage drop next to this table, because you're gonna be coming here to get that, you know, just about everywhere, except, well, on every problem. Okay? Everybody follow with that pretty much? Yeah, okay. All right. This line here being a division line, right? This line here being a multiplication line. So in this case down here, this is multiplication up here at the top, these two numbers against each other. Really do it the same way. If you put a whole bunch of lines in there, it's really the same thing. But to keep it visually where you can see what the relationship is, it's better to do it like this, so you can kind of see that that's the same thing that you see with the VAR and the WAV. It's the same kind of mathematical relationship in a visual take. So it's 6.5% then is the loss, which, here's what we're talking about the voltage drop. If we're looking at a kind of a diagram, I guess, so to speak, you're trying to see that the total value from your point of service to the very end of it, we don't want it to be more than 5%. So that means that if I've got a distribution panel here and a marker that doesn't really show you much, I do that all the time. I'll throw them down, and at the end of the class, I'll be like, oh, here's a brand new marker. What's going on for it? All right, so 5% then from here to the very last farthest point load on the entire thing, entire service. 5% max. So that's the distribution point. 5%. They also tell you, you know, in the section that deals with this, is that from your last breaker, or your last point of overcurrent protection device, to this end, not more than 3%. So our branch circuit calculations, then on the branch circuit side, if it's got a breaker, only one breaker of any kind to the very last point is 3%. If I've got two breakers involved, then it's feeder and branch circuit. If I've just got from breaker to breaker, then I've got feeder. And so mathematically, they don't tell you this in the code book, but it goes to say that that's 3% and that's a max 5%, this is going to be 2%. So this is feeder, this is branch circuit. Okay? Now, on the test, the little sheet that they pass out, they get it backwards. Beats me. Tells you how good they are with well, the people that are doing the test themselves, the paperwork they've got is kind of screwy, but just don't pay any attention to it. They've got, in fact, I think some of them have scribbled out, so I think either the electricians have gone through and tried to help the next guy down the line, or maybe the people who work there finally got a window. But at any rate, it's 5% total, 3% on the branch circuit. And most of the time you're looking at this stuff, it's a branch circuit calculation. So let's do number 2, which is we've got a voltage drop across a different circuit, but now we're asking you, actually that's a 3-phase, I don't remember that one, sorry. Number 3. Number 3 is a single phase, and so on that problem, we'll come back to it here in a minute, because if it's 6.5%, it's a little too high, but if we're looking at number 3 here, what's the maximum length of conductor is the next type that you're going to cross. So if this one is voltage drop, and I just kind of erased it or hit it or whatever to perform whatever's left over, then define a wire size, I'm going to do the same thing, but I'm just going to erase this one. Mechanics remain the same, though. I'm still going to take this top line, which still is the same number, what was it, 128,000 or whatever it was. Actually, it'll change because I'm using different numbers here. I've got a number 10, 30 amps, and, ooh, go work that out for yourself real quick and see if you can, I'd like to see what you'll make out of that one. We talked about something yesterday that you have to keep in your mind when you're doing this one. And that's really that's probably the best example of one that actually you might actually use sometime down the road in your trade.
One question. For the formula, the D, sometimes in the question it said one way.
Mm-hmm.
If it says two way, you're gonna take off the two?
Yeah, if they say the distance is the both directions, then yeah, you'd have to.
Just drop off the two?
Yeah, but you have one on. I haven't seen one on a test. I haven't heard, but it'd be
Oh,
tense.
it say one way?
Yeah. Yeah, it's that, and you do have to be careful of that, because sometimes they give you the length of wire is 200 feet. If the total length of wire is 200 feet, well, really your distance then is 100 feet. Make sense? So, thank you for bringing that up, that's actually a good point to keep in the back of mind.
I think it's
No,
this.
there is a table here.
Oh,
Sorry, I lost page 741.
Yeah, we're doing.
3?
So this is the formula they're gonna use right here. What do we plug in right here for this VD? You can't put anything in this formula that's not a real number. A percentage is not a real number.
0.05.
7.2, would be 3% since the brain shirt
It's 3% of what?
of